Send me a 16-bit 44.1 kilohertz WAV file to my cloud server and an MP3 file at 160 kilobits per second in an email. How's that again? Okay, you've performed your first voiceover gig from your home voiceover studio, and it's time to deliver your performance to your client. Way back in the day, you would mix it down to quarter-inch tape and FedEx it for next day delivery. But whoa, that was the last century. Today, physical copies have gone the way of MC Hammer pants. Everything's digital. And you need to learn the lingo and jargon, and moreover, the concepts represented by these words to communicate effectively with your clients and deliver your work in the format that they require. So you need to understand and speak digital. Okay, if you know this stuff, you can skip this part. But if you're not sure, clear your mind and settle in, because I'm going to explain digital recording once again. So what is digital recording? Wait a minute. For that matter, what is digital? Let's start with that. Representing information in a digital format came out of the computer industry. Computers store information with little switches, sort of like the light switch on the wall. Now, that on-the-wall light switch only has two states. It can be on or off. These two states can be represented with just two digits, a 0 for off and a 1 for on. In everyday life, we use a base 10 number system, which uses 10 digits to represent any number. But what if you only have two digits? Well, to represent numbers with two digits, you need to use a different number system, a base 2 number system. This is the renowned binary number system. There have been thousands of articles describing how binary numbers work, but suffice it to say that we can represent a base 10 number like this with a binary number like this. And that representation of the number can be stored in those little light switches. Let's see. On, off, on, off, on. Well, you get the idea. By the way, each of these little ones and zeros is called a binary digit. And since they're little tiny things, and because technical jargon often has some word humor in it, the term got shortened to bit. A binary digit equals a bit. These binary digits were often worked on in groups of words of 8 bits. So if you had one group, you would have one word by 8 bits. 6 words would be 6 words by 8 bits. Well, it didn't take long for those merry computer folks to shorten by 8 to byte. Get it? Like byte. A bit and a byte. And 4 bits was called a nibble, but you'll rarely hear that term anymore. Yeah, those computer labs are a virtual comedy store. So now you have a number system that you can store in a computer's memory. How do you convert sound into numbers? Let's start with a quick analogy. Suppose we want to map the peaks and valleys of a mountain range. One way to do this would be to walk along in a straight line and every few feet take an altitude measurement. Walk 10 feet, measure 5,234 feet. Walk 10 feet, measure 5,245 feet, and so forth for the whole mountain range. This would give you a series of numbers like this, or in binary like this, that you can save in your computer. And by recalling these numbers, you can redraw the peaks and valleys of the mountains. Now let's look at a sound wave. Here's a typical sound wave. Wow, that looks just like a mountain range. Well, at least like a mountain range reflected in an alpine lake. So we can measure the sound wave in a similar way. Move along a wee bit from left to right, which is called the time axis, and every few moments take a measurement of how high or low the waveform is, which represents how loud the sound of the waveform is. Amplitude for you science buffs. Once again, you get a series of numbers, like this, or in binary, that you can store in your computer to represent the audio waveform. And if you spit these numbers back out at the same rate you recorded them into a device called a digital to analog converter, presto, you hear the same sound you recorded. Ah, digital recording. Now, you don't really need to know exactly how all this happens, but understanding the general principles will help you make sense of all the digital recording terms that are tossed around. Here are your first terms: sample rate and sample format. Let's go back to our pleasant stroll along that mountaintop and look a little closer at what we're doing. First of all, we rather arbitrarily decided to take an altitude measure every 10 feet. But what if we took a measurement every 5 feet? If we did that, the representation of the mountain would be more accurate, wouldn't it? And if we took a measurement every 20 feet, the representation would be less accurate. So if we're walking at a steady pace, the accuracy is determined by how often we take a measurement. The techno term for taking a measurement is called taking a sample or sampling. And how often you measure is called the sample rate. Then there's the other piece of information we collected: how high the mountain is. Remember, we measured it in feet. Sorry, rest of the world. But what if we'd measured it in inches? Then the measurements would be 12 times more accurate. But what if we measured it in yards? Then the measurements would be less accurate, 1/3 as accurate. So the accuracy of our height measurement is determined by which unit of measurement, which ruler we use. The techno term for the number of units that you use to measure is called the sample format. So let's apply this to digital audio. We'll look at sample rate first. Obviously, we don't walk along 10 feet. We walk a lot faster. In digital audio, we actually measure several thousand times each second. So the sample rate in digital audio is expressed as how many thousands of samples there are in each second. Samples per second. For example, CD quality digital sound has a sample rate of 44,100 samples per second. And since this stuff was all made up by scientists, the number is usually expressed with a decimal and the term kilo, which means thousands, and the term hertz, which means times per second. So we would say the sampling rate of a CD is 44.1 kilohertz. That is 44,100 times per second. So how about the sample format? Notice that we measured the mountain altitude. The height of the mountain at a particular point didn't change, but the number we used to represent it changed depending on which scale we used. So it could be 1,748 yards, or 5,245 feet, or 62,940 inches. So we're actually dividing the overall height into smaller and smaller and more units. And the more units we use, the more precise the measurement. Digital data achieves this increase in accuracy by using more and more bits to represent the waveform height. Remember, a bit is like one light switch, and digital numbers require 1 bit per column. 1101 requires 4 bits. 1001, 1010 requires 8 bits, and so on. Using more bits lets you divide your measurement into more and more smaller parts for more accuracy. For you math freaks, this relationship is computed by using the number of bits used as the exponent of 2, because it's binary, right? 2 to the power of 2, 2 to the power of 3, etc. So you see, when you use more bits, you get more accuracy. This additional accuracy translates into clearer sound with less noise, or hiss. For you audio purists, each bit gives you an additional 6 decibels of theoretical signal-to-noise ratio. And this is called the dynamic range. So 8 bits gives you a dynamic range of 48 decibels. 16 bits gives you a dynamic range of 96 decibels. And 24 bits gives you a whopping 144 decibel dynamic range, which is wider than the range of human hearing. So when they invented CDs, they had to pick the number of bits. They figured 96 decibels was pretty darn good. So they settled on 16 bits as the CD sample format. Aha, the sample format and the sample rate. When the numbers are thrown around, they are usually expressed with the sample format first and the sample rate second. So the original sound data recorded on a CD is 16-bit, 44.1 kilohertz data. By the way, this is the most common data format and rate used to send files to clients. So if they don't have a preference, use this. Another common format is 16-bit, 48 kilohertz. This is often used on video editing systems. You can also save this audio data on your computer in exactly the same way. This happens when you rip a CD track to your computer. If you save it to a PC computer, you will create a .wav file, pronounced wave. If you save it to a Mac, you might create a .aiff file, pronounced AIFF. Sorry. Trust me, you will never need to know this, but this type of recording is called PCM, or Pulse Code Modulation Recording. If the sample format and sample rate are high enough, it can accurately record sound beyond the range of human hearing. For example, 24-bit, 96 kilohertz recording can record a dynamic range of 144 decibels and a sound spectrum from 20 to 48,000 hertz. They came up with this method of recording to accurately record the best possible sound without any of the hiss, rumble, wow, and flutter that was inherent in mechanical recording on tape and vinyl records. And as an added bonus, when you send a digital file to someone, you're not sending them the sound. You're sending them the numbers that represent the sound. So you can copy the digital data, and then copy that copy, and then copy that copy of a copy, etc., 1,000 times. And each copy is an exact replica of the original. And you can do all those cool things you do with digital files. Store it on your hard drive, upload it to a website, download it, save it on a thumb drive, etc. So for fancy projects that want the best audio, WAV files are the way to go. There's only one problem. These files are big. I mean really big. 1 minute of 16-bit 44.1 kilohertz mono is 5 megabytes. A 30-minute narration track may be 150 megabytes. And if you have multiple takes, it's not unusual for the files of an audio project to be 500 megabytes to several gigabytes. Here's one time when you have to sound like you know what you're talking about. When the client says they want WAV files emailed to them, you need to correct them. Quote, WAV files will be too big to email. Unless it's only one take of a few seconds, the files will swamp their email if you send it, and it will likely be rejected by the mail server. Fact of life. Don't let them argue the matter. Don't email WAV files or AIFF files. So what's a voiceover artist to do? Don't panic. There are solutions to the problem. Either send smaller compressed files, we're talking MP3s, or upload the uncompressed WAV file to a cloud server like Google Drive or Dropbox for the client to download. I'll talk about MP3s and the cloud in my next video. If you're interested in working in voiceovers, take my free voiceover lesson. I give a quick overview of the voiceover business, and then you perform a voiceover commercial with my notes on how to make your interpretation really stand out. And you can upload an MP3 of your read to receive my personal evaluation. The link is in the description. And for information on my live and online voiceover classes, and live coaching and demo production, and all things voiceover, go to alisocreek.net. If this video was helpful, hit the like button to help others find it. Then subscribe and hit the notification bell so you don't miss my future videos. I'm William Williams reminding you, keep talking.